Hello guys, today is my first ever online lecture course on physical chemistry 1. So we will be talking about enthalpy, uh, calorimetry, and how do we measure those energies that come and is present on every reactions that we encounter on our chemistry subject. So uh, let's start. Our topic today will revolve around enthalpy and calorimetry, the concept of energy, then we will talk about the enthalpy, calorimetry, and how can we measure those heat and energy that is present on every reactions that we encounter. There are actually two types of uh, calorimetry, the coffee cup and the bomb. What are they? We will discuss it later on. And the computations on the thermodynamic behavior, thermodynamic problems. Okay, but first we need to define the concept of, we need to know the concept of energy, I should say. In some textbooks or in all textbooks, energy is the ability to do work. We all learned about the energy in our past lessons that it is a concept that drives everything in the universe and is defined by physics as the ability to do work. Okay, that definition was seen to be applied in mechanical systems. However, it can be used in chemical systems too. We all know that because in chemical systems, when we are doing chemical reactions may either release energy or accepts energy. Well, common conception of energy is the push or pull of an object. It's all how we know it, but of course not all. Yeah. That's based on the physics definition, ability to do work. We also utilizes energy for the modes of transportation, and then we use it, of course, to cook. We previously studied about the concept of energy as it cannot be created or destroyed. That's according to the first law of thermodynamics. Energy just converted into one form into another, this. Uh, just like this, how does this train work? It converts those chemical energy. This chemical energy was used from the fuel that it had, or the electrical energy if it is an powered train, into mechanical energy because it will start to move. Also, by means of pushing and pulling, so our body utilizes chemical energy present on the in our body and eventually use it to move the crate and create some sort of mechanical energy to move them. So that's how the energy works. Energy cannot be created or destroyed. And of course, chemical reaction also needs energy to proceed. Either it needs or it releases. Okay? So in our case, we have here the synthesis of, or the formation of hydrogen peroxide. So with the delta H or enthalpy of formation of 187.5 kilojoule, which is actually positive. Yeah, it is positive, meaning that it is an endothermic process. Just remember the conventions that I taught to you in the past lessons. When it is positive or negative, it has something to say. If the reaction is endothermic or exothermic. Yeah, we already talked about the endothermic and exothermic reactions. Endothermic reactions usually requires energy, and exothermic reaction releases energy upon reaction. Well, but the question is, how is this why is there is an energy need or release upon a reaction? So it happens. Let's try to view this reaction by means of molecular model. Okay, we have here H2 or hydrogen gas, and also here we have here O2 or the oxygen gas, and then forming hydrogen peroxide in liquid form. And then let's determine the reactants and products. So in reactant, we have here H2 and O2. And for the products, we have here the hydrogen peroxide itself. Now, let's take a look at these bonds that are present on our products and reactants. I will try to highlight it using yellow pen there. Those bonds are responsible for whether the reaction will go endo or exothermic. Okay. When we look upon these bonds present on these reactants and products, uh, okay, first, let's think how can we break those bonds, okay? We are referring here as the bond dissociation enthalpy, if you are all familiar with it. This bond dissociation enthalpy refers to the amount of energy to break the bonds present in our products and reactants. If the bond dissociation enthalpy of the product is greater, so according to the Hess law, it should go endothermic. Okay? If the bond dissociation enthalpy on the reactants is much higher than that of the products, then the reaction should be exothermic. That observation greatly obeys the Hess law regardless of the direction of the direction of or the sign convention of individual energy bond enthalpies. So it's only a matter of energy. You should say energy cannot be created nor destroyed, as the first law of thermodynamics tells you. Okay? This means that energy can just be transferred from higher energy body into a lower one, and then they achieve thermal equilibrium later on, and also it the concept of energy implies that the energy was just transformed from one type to another. Okay, let's try to recall the first law of thermodynamics, and according to that law, the internal energy of the system is equal to the heat and the work present. And also, don't forget to put the sign convention for the Q, whether it goes in or goes out the system, or work, whether it is performed to the system and performed by the system. Okay? For calorimetric problems, we will be mainly looking at here the Q. Okay? This Q will pretty much tell us about the nature of the thermodynamic properties of the reaction that is happening. Either it is an endothermic or exothermic reaction, and also with respect to the non-state variables present, such as the pressure, volume, and the temperature. The original formula, according to the first law of thermodynamics, for the internal energy is the sum of the heat and the work of the system. Okay, we know that work is equal to negative P dV, right? So by rewriting the equation for the internal energy, the change in internal energy, du is equal to Q plus negative P dV, or just du is equal to Q minus P dV. Okay, we will be looking here at the Q itself at two ideal gas processes such as at constant P and V, which is for the isobaric process here, the isobaric and the isochoric process. At isobaric process, Q can be written as QP, which is equal to the delta H, or the enthalpy itself. And we know that in isochoric process, the QV refers to the heat at constant volume, which is equal to U. Okay? But I will try to rewrite this one on form of differential. Okay. But let's try to focus here on the QP part. So substituting this to the Q on the original equation, so we got here du is equal to dH minus PB, right? So that is the equation, but we need this. Let's equate the equation to dH. So we will get dH is equal to du plus PB. So this is a standard enthalpy formula. We will use it to compute for the PB work here, and the du. Okay, and also we can also get mainly the dH. Okay, by means of this equation, we can just compare or relate the dH and du, or the enthalpy and the internal energy of the system, and how does the PB here affect the system. Okay, let's try to clear everything up. We will try to isolate those the formula that we got. Okay, so let's continue. So we can equate this PDV by using the ideal gas equation into, assuming that this is a constant pressure isobaric process. PdV is equal to nR dt. Okay, so we can substitute this equation here to there, so giving you dH is equal to du plus nR dt. And further, integrating this two sides of the equation to H2 to H1, U2 to U1, and T2 to T1, you will get delta H is equal to delta U plus nR delta T. From this equation here, we can use this if we want to know the effect of PB work of compression of the gas and or the expansion of it. But this is only used for gaseous samples or compounds. Why is this so? Because if we look at the solids and liquids, you know that their volume was not, it is not like the gases, because the gases tend to push themselves apart, far from each other. So if we have a liquid and a gas, it is not, the volume change is not much significant, and because of that, this dV here is equal to approximately 0 for liquid and solids. And because of that, in consequence, for liquid and gases, the delta, the dH is approximately equal to the du, because the PB work here is not that significant. Okay? And for a certain reaction, we will be looking here the NRDT. Actually, at a specified temperature where just a given T, we can rewrite this formula into dH is equal to du plus delta N. That's because the amount of moles of gas in the reactant and product may differ. So this delta N refers to the change in the N of the gas of the product minus the N of the gas of the reactants. That corresponds to the change in the moles of the product to the reactant part. Okay? And I forgot to bring the RT. Okay, so we will use this formula to calculate the delta H of a given chemical reaction. Oh, by the way, I'm just talking about the gaseous moles here. So I'll be just referring to the gaseous moles of the product and the reactant. So the liquid and the solid reactant will be disregarded. In addition, so since we derived this equation here on the ideal gas equation, so we need to take into account that the gas should be ideal. Okay, so this is not applicable for real gas systems. Okay, let's start to calculate the delta U of the reaction, given that we have the first, on the previous slides, we got the formation of hydrogen peroxide. So let's try to calculate the delta U for this. So given that we have a delta H, which is a delta H of formation. I just want to tell you guys that the given standard enthalpy, regardless it is formation, combustion, etc., you need to take note the temperature or the pressure it was given. So this example was taken at 298 Kelvin, 0.15 Kelvin, and 1 atmosphere. Okay, so always take note of the variables that it was taken. So okay, solving this, we need to write the formula. Delta H is equal to delta U plus delta NG RT. Okay, so the temperature that this was taken was 298.15 Kelvin. So let's plug in those given. So first we need to calculate this delta NG. How can we calculate those NG, which corresponds to the change in the moles of gas, the reactant to the product. So since there is no gaseous product present, so we can write this down as the N of gas of the product is 0 minus for the reactant. So we have here 1 mole of O2 and 1 mole of H2. So that will make it 1 times 1 for the say O2 plus 1 times 1 for the H2. So we get 0 minus, that's 1 plus 1, which is equal to 2. The change in gaseous moles is negative 2 mole. Okay. So given that we have a T or temperature of 298.15 Kelvin and a delta H of formation of 187.5, kilojoule per mole. Okay, so let's try to calculate the delta U. Rearranging the equation you get here, let me change the color of the pen. We get here delta U is equal to delta H plus NG RT. Okay, so that would be delta H, which is 187.5 kilojoule per mole, plus the delta NGRT, which is -2, or of 8.314. Take note that we use 8.314 whether we calculate everything that involves energy, and the temperature is, can I just write it down here? The temperature is 298.50. So okay, calculating those, we get 187.5 kilojoule minus, because it's -2 literal. Let's try to calculate this right part. It's that's -2 times 8.314 times 298.15 give us since it was a kilojoule, this is 4.98 kilojoules. So oops, 187.5 minus 4.98, that's 182.52 kilojoule. Oops. So that is the internal energy of the system. Okay. Well, using this formula, we know that how we can compute for the delta U just by looking at the relationship of delta H and delta U with regards to the change in gaseous molecules present on the chemical reaction. Okay, given at certain temperatures. Just a quick review: the heat refers to the transfer of energy between objects due to temperature change. If there is a change in temperature, there is a heat flow, of heat or transfer of heat between two bodies. Okay, if there is no contact or no temperature change, there is no transfer. Okay, so there are two types. We already know this. The exothermic process, whether you have a system T1, it releases heat to the surroundings T2. In consequence, the system will go cold because it releases heat, and the sign for that is negative Q. Another is the endothermic process. The system is relatively colder to the surroundings, therefore the heat will flow to the system. Always take note that the movement of heat is from higher to lower. Okay, that is spontaneously true, but upon introduction to the Carnot engines and the engines, we will encounter that the heat can flow from a cold to hot just by introducing work. Let's consider two adjacent systems. Okay, we have here a hot water on the left, a system on the left with the hot water 90 degrees Celsius, and on the right side we have here a system with a cold water at 10 degrees Celsius. We have here an insulated box, meaning the transfer of energy to the outside of the box is not permitted, but there is a diathermic thin wall present in the middle separating the two systems, which permits the transfer of energy between the two. Okay, we know we have here a hot water and a cold water. So meaning, if we look at the transfer of energy, we know that the track here is from hot to cold. So meaning it will go here and spontaneously not here. Okay. So if you consider this system, when the transfer of energy from the hot to the cold spontaneously achieves what we call TQ, or the thermal equilibrium. TQ. This is the temperature at equilibrium. If the temperature of the hot water or the system on the left will be equal to the temperature of the system on the right, then we can say that they achieve the thermal equilibrium. Okay, so that's the T system 1 is equal to the T of the system 2. Well, always remember that the thermal equilibrium for this is when the temperature of the system 1 is equal to the temperature of the system 2. In this part, the change in temperature from the starting to the final temperature of both systems are studied in order for you to compute the Q. This Q refers to the heat that flows from a system to another. And in this part, synonymously to in conjunction to the first figure that I've shown you, let's consider here a system 1 and system 2 at 25 degrees Celsius. Okay, so let's if we consider here adding, okay, let's say, I guess, water. So let's try to add here water. Okay, this is the water. Okay, let's try to shade this. Okay, and let's try to add also water here, but they are separated by a wall, huh? Don't think that they are sharing those waters. They are separated by a wall. Let's say on the system 1, let's say on the system 1, we will be adding here sodium hydroxide. Okay, so the sodium hydroxide is here, let's say a certain amount of sodium hydroxide pellets. Okay, we know that if we add sodium hydroxide to the water, those are, okay, let me label it up. If we add NaOH to the water, we know that the reaction, the dissociation of NaOH is a very highly exothermic process. It releases energy. So upon the dissociation of NaOH, it will make the temperature rise. So the heat from this will be the heat of the dissociation of NaOH will make is an exothermic process. So, and that energy is being given to the water on the system 1. So in return, the temperature of the system 1 will eventually increase. Okay, since there is an increase in temperature of the system 1, and you know that we have a wall here that permits the transfer of energy, then those energy or the temperature difference, those heats will be transferred here, and then eventually the system 2 temperature will also increase. Okay, so usually this technique was actually utilized in the laboratory in order for us to determine the Q of the reaction or the heat of the reaction. This process is called, you know it, and calorimetry. Okay, but usually we add here a thermometer. The role of the thermometer uh, is to measure the change in temperature over time as the reaction of NaOH goes by. So meaning this thermometer, the temperature of this system 2 will eventually rise, that increase. So this is the initial one, and this is the, this change in temperature refers to the delta T. Okay, so this delta T is very essential to quantify the amount of energy released by the dissociation of sodium hydroxide, which is transferred upon to the system 2. By the way, since the system 2 contains water that actually receives the energy, this water refers to the to as heat sink. Okay, and from this we can calculate the Q with the if we observe the delta T by using the formula Q is equal to mc delta T, where the C is the specific heat or molar heat capacity. Take note guys, specific heat and molar heat capacity is different. No, specific heat was directly related to the amount which is expressed in grams. Okay, but the molar heat capacity refers to the moles per mole of that compound. Okay, so okay, I give you an introduction of the calorimetry. So what is a calorimetry, by the way? It is a measurement of heat involved in a physical and chemical process by monitoring temperature changes. Okay, so that's the role of the thermometer here. So it monitors the temperature change in the system. Okay, the principle of the first law of thermodynamics was applied throughout, which is mainly the energy is conserved, meaning the summation of energy is equal to zero, meaning the energy of the reaction can earlier given an example of a dissociation of NaOH in water, which is an exothermic process, and the sum of the energy that and the energy that accepted by the system 2 or the heat sink is actually zero. Okay, so this two formula, the summation of Q0 and was very useful in determining the Q of the reaction. Okay, so we can also express this in terms of Q Rx, and Q of the reaction is equal to negative Q H2O. This heat refers to the heat of the reaction, or the heat accepted by heat sink. And the Q of the reaction here is the heat of the reaction itself. What type of Q of dissociation? Okay, but it is not always dissociation. You can the reaction can also be combustion. So the Q reaction will be the Q reaction combustion, or the Q of the reaction if it is formation. So that is it depends on the type of the reaction that happened. Okay, but this is only true for adiabatic system, because we are in adiabatic system there is no energy lost to the surrounding, so we consider here an isolated system. Okay, and we took the system as isolated adiabatic. We need to assume that the heat wasn't flowing out the system. Okay, how can we measure the heat flow? We use a device called calorimeter. Okay, so there are two types of calorimeter. a BAMCAL, and a coffee cup. I know that you are familiar with the coffee cup calorimeter. Uh, we use here uh, a, a standard coffee cup, okay? But on a BAM calorimeter, this is rather relatively more complex than the coffee cup calorimeter because this one is very isolated compared to the coffee cup, because coffee cup is eventually we can't uh, in real case scenario in coffee cup calorimeter, uh, the system is really not that adiabatic. And take note, we are using here the formula Q is equal to mc delta T, okay, where m is the mass, the C here is a specific heat, the delta T is the change in the temperature. We can also use that in Q is equal to NCP M dt. What is this? This Cp refers to the molar heat capacity, which is different expressed on the mole, expressed unlike the C here. The C is specific heat expressed in grams. Okay. The most common heat sink used was water. We can also use the calorimeter itself. Okay, and the actual value for this is for water used as a heat sink. The value for C is 4.184 or 1 calorie per gram centigrade degree. But and also take note that the actual value changes at different temperature experimentally. Okay, the value depends on the type of calorimeter for the C-cal. So for calculating the Q for the calorimeter, we use only C-cal delta T. Okay. Okay, so we have here the BAM calorimeter. On the figure on the right is an actual picture of the calorimeter, the BAM calorimeter system. We have here the motorized steer, which were upon ignition wires, the thermometer, insulated container, sealed bomb, O2, gas, sample cup, water. So what happens here is that a sample cup that has a sample in it was actually put in a sealed bomb. This sealed bomb here, a specialized compartment for the reaction. So when the reaction occurs, it will release energy to the surrounding, and that surrounding refers to the heat sink here as the water. And then after that, those heat will be measured by the thermometer. On the figure on the left, we have here the process or the heat transfer process on the BAM calorimeter. We know that this wall here, the walls present to the BAM cal is actually insulated very well. Okay, and also for the BAM calorimeter, we can easily compute for the delta U because the heat present here is at the constant volume. Why? Because if we have here a constant volume calorimetry, it refers to the dH, U plus P the dV. This dV at constant calorimetry equals to 0. So this is significant though. And this du is equal to dH, which is just the QV or the heat at constant volume. Okay. In our humble coffee cup, okay. In a coffee cup calorimeter, we assume here that the delta H is at the constant pressure in an isobaric process. Okay. The part of the coffee cup calorimeter was there is a thermometer here to measure the change in temperature. The stirrer, okay, and the nested insulated cups, or we have here the reaction mixture. So at first, you put the reactants in the reactants there in in this reaction mixture, and then you let the reaction, and then the change of the reaction here at the mixture will then be recorded by the thermometer. On the left, this is the thermodynamic transfer process for the coffee cup calorimeter. Okay, let's try to solve a problem. Okay, a chemistry student dissolves 4.51 grams of sodium hydroxide in 100 ml of water at 19.5 degrees Celsius in a calorimeter. That's a coffee cup calorimeter. As the sodium hydroxide dissolves, the temperature of the surrounding water increases to 31.7 degrees Celsius. Determine the heat of the solution of the sodium hydroxide in joules per gram. So we have here in joules per gram. Okay. I'll try to give you time to solve. So just pause the video and come back after you solve the problem. Okay, so I guess that you have an answer. Given that you have a 4.51 grams of sodium hydroxide reacted to the water itself, so we will just compute for the amount of heat that the water, or just the heat sink, recorded. So the the T1 of the water is 19.5 degrees Celsius, the T2 is 31.7, and the specific heat of water is 4.184 joules per gram centigrade degree. We know that the Q of the sodium hydroxide reacting to the water, or the dissociation of the sodium hydroxide, is equal to the negative Q of the calorimeter. Well, since there is no given Ccal, or the specific calorimeter, specific heat of the calorimeter is given, there's no given, such as the heat sink here is actually the water. So that would be QNaOH to the heat sink of QH2O. That is that is Q NaOH is equal to negative MCH2O delta D. Okay, so that is 100 grams of water, that because 100 ml is equal to 100 grams, because the density of water is 1 gram per ml. Okay, the CH2O is 4.184 joule per gram centigrade degree, and the delta T here is actually 31.7 minus 19.5. Okay, so 100 grams times 4.184 times the change of 31.7 minus 19.5 is equal to 5104.48 joules. Okay, this unit would be in centigrade degree, so that's cancelled. The gram here is also cancelled. What we have left is the joule, or we can express this at 5.1 kilojoule. Okay, so I leave this. Okay, I just leave you the problem here. Try to answer this, and just message your answer to the Google Classroom, and I'll be seeing you on the next topic. Thank you for listening. Have a pleasant day and always keep safe.